Good.
Okay. Welcome everyone to this wonderful day. I am Gaurav Jain, Junior Data Scientist at HMLE AI Labs. I'm joining this webinar from New Delhi, India, and it's already twilight here with 10 degrees Celsius, shivering cold. And we are again back with another webinar in the series of HMOI Machine Learning Externship 2021. So, as you all know, machine learning without deployment is just like food you have but you cannot eat. So, keeping that in mind, today we are back with webinar with Mr. Charles Etitoloi, CEO of Maven Code LLC, who will be sharing his thoughts and guiding you on the topic transformation, industrial transformation with machine learning using Kubeflow. So, before starting, just a few housekeeping rules. The webinar will last for an hour and 30 minutes. To ask question, please use the event code hashtag 28920 on slido.com and they will be promptly attended by our faculties and associates. You can also use chat boxes on Zoom and YouTube to share your thoughts and ask your questions and actively participate in this webinar. In case you want to speak, please raise your hand and you will be unmuted. So keeping your excitement high, I would like to call upon Emmanuel, Associate at Hamoy, to take on this webinar further. Please feel free to ask questions on the chat boxes. Emmanuel, over
Yeah,
to you.
thank you so much, Ura. It's a privilege, to have this session today, and it's a privilege to have Charles Adetiloye with us. Unlike the 10 degrees in New Delhi, I'm joining the call from Lagos, and it's about 31 degrees here. It's actually a very sunny afternoon. But let's proceed to meet our resource person and our speaker for today. Charles is the co-founder of Maven Code. And Maven Code is actually a provider of consulting services and expertise for building and implementing large-scale distributed reactive backend systems for processing massive large-scale data sets. It is based in Salt Lake, Texas, and we are privileged to have the very own CEO here with us today who will share from his wealth of experience with all of our students and all of our participants. Charles has well over 15 years worth of experience consulting, implementing large-scale data processing in AI and ML software platforms across different industries, vertical actually. And now previously he's worked on Lightbed, he's worked on Twitter, Starbucks, and a few other startups and Fortune 500 companies. It's actually a privilege to have a colossus of the machine learning industry here with us, and who he has come to help our students grow to that level of machine learning expertise. So Charles, it's a privilege to have you, and I'm sure our students will love this moment. Over to you, Charles. Let's be blessed with your words. So before we take on Charles, okay, I think it's before we start listening to the blessed words of our beloved Charles. I think first of all, let's share, between the last 10 days, how the externship has been. For some of us, machine learning is a new field. It's a new area that we're delving into. For some of us, we've had quite an experience with machine learning, and coming over to Amoy Machine Learning Externship, it's a way of changing the stance from beginner to expert level. So while we wait on Charles, let's get to share a few of our experiences so far. If for those of us on YouTube, please go on to the chat boxes on YouTube, the chat box on YouTube, share your experience with us, and let's get to enjoy the blessings from your end as well. So I expect to see some of our comments now on, yes, on Zoom, on the chat boxes. So Ekun Kelvin, Frank, Happiness, James, Helen, Henry, Fiora, let's get to hear you share your thoughts in the chat box. And now, first of all, um, I want to acknowledge that from my own experience, uh, the extension has started on a good note. And I'm sure even the MOE team members can agree that it has been wonderful in its regard. Questions coming from different angles, a lot of confidence being shown from our students. And I'm sure that these 4 months that we're going to be spending here, will be the start of something great to, to proceed with. So we have some comments already coming in from YouTube. But then I think before I read the comments from YouTube, let's ask somebody. Joe Brands.
Hello.
Yes, Joe Brands was part of the internship last time, and this time he's a volunteer. He's helping as a member of the MOE team, and he's also one of the 18 members that's handling a learning community. So let's catch your experience in say 2 to 3 minutes.
All right. Well, it's been a wonderful experience, if I must say. Well, I may back up a little bit by just saying what I had as an experience in the last internship I had. It was a moment whereby I had to learn to stretch myself in a lot of things. And I want to believe that is what, even much more, what the current students are going to experience. So it's been a wonderful thing, a wonderful experience. Then currently, a couple of days now, being a volunteer, it's lovely. I mean, seeing people that are yearning to learn, asking sincere questions, because sometimes when you come into something that is new, you are lost. You don't even know where to start. So, and one of the ways you can find your way is by asking just simple, sincere questions. And that is what I've seen that's been happening with the current group of students we have. So Harmony has been a wonderful company, school, whatever you call it. And I couldn't hold back to anything I could give in any way I could. And that is why I decided to volunteer at this time. So thank you so much, Emmanuel, for the opportunity.
Wow, thank you very much, Joe Brandt. So it's exciting, but before I allow you go, I still want to ask you one question. But then let's hold off for a couple of seconds. Henry Ifiora, he's saying it has been a good experience so far, though it's a new territory for me. I assure you, Henry, that in a few weeks the storyline will change. So thank you very much. Joe Brand, so for people that for Henry and others that are new to machine learning, what are the steps that you would advise them to take, especially at this stage of the extension, so that the same way you survived the internship and became very good at what you do now. So what advice would you give to them so they can improve?
Well, my simple advice is just put yourself in a learner mood. That's first. Be willing to always ask questions, be willing to learn. But just make up your mind, you yourself, that you have to learn. Just possibly, if for those that are new to this, is a new field, then do other things you can do even outside. Now, that means you need to read, you need to do more research, you need to look at a couple of YouTube videos and all that at your own time so that you can learn what is being taught in the class, because it's going to be overwhelming for a lot of people. But for me, it was overwhelming in the first course. But after some time, I started to understand, because by the time I understood the basics of Python, it now made it easier for me. So I could now start applying what I've learned, and I kept expanding from there. So just make up your mind that it's something you can do. Yes, it's overwhelming in the beginning, but just tell yourself, yes, I can do it. If Joe Brandt can do this, if one other people can do it, then I can. So that is the attitude you need to adopt at the first. Then be willing to learn. go to online, search out some things. I type a lot of questions online on Google, try to learn something. When I'm encountering problems with my codings and all that, I just go online and type something, and I somehow I get solutions to that. Sometimes I also ask people on Slack. Okay, my fellow
Yeah.
interns, I have to ask them. I mean, I'll keep asking them. I never leave them. Even privately, I just ask them, what do you think about I'm having this kind of problem? So it is something I know you can do. It doesn't matter what your background is, your
Oh,
economics,
that's
whatever. It doesn't mean anything. You can do it. Trust me,
thank
you
you.
can.
Wow. Thank you, Joe. Thank you, Joe. I am also blessed. Thank you. We would have loved to continue this session, but man, also need to learn about industrial transformation of the machine learning world. So we have Charles back on and he's ready to take up DJs. Yeah, put Joe's advice on your paper and put it in your mind as well and learn from this. So Charles will give us the blessings of the day, and I'm sure that we'll have a wonderful session. Thank
Hey
you,
guys,
guys.
yeah, sorry about that. I was having some technical difficulties joining, but I think I'm on right now. So sorry for the glitch.
Thank you, Charles.
So just give me 1 second and I'll pull up my screen and we can get started. Yeah, let me know when you can see my screen and we can get going.
Yes, Charles, you can see your screen.
All right, good.
Yeah, thank you.
So today we're going to be talking about some of the areas of machine learning, interesting areas of machine learning. Yeah, it's been there for long, but I don't think most people would think this is applicable as well. This industry too can leverage on a lot of things that machine learning does. So think about all these industrial equipments that build all these big things that we enjoy every day. Industrial equipment that they use in manufacturing processes, chemical processing plants and stuff like that. Everything is good until something goes wrong. The whole idea of using AI and ML is for AI to be able to understand when a particular equipment is going to fail, and you can easily predict that that part of the machine is going to fail or not. So in any industrial process, there are many systems and subsystems that are all connected together. And all this system works, and it takes many people long years of domain experience working with that machine to know if something is going to go wrong. So what happens if they hire you as a fresh graduate or a new employee to like manage all these machines, and you don't really know what goes on? So that's where AI comes in. So using AI, we can study the behavior of all these machines over time and be able to predict if something is going to go wrong. So that means you understand the normal operating behaviors. And if anything goes out of the norm, then you can easily go back and see like, oh, we need to fix this part of the machine. That's likely what's going to go wrong. So with AI and ML, every time that machine is running, they generate different kinds of events. It could be that like the torque, it could be the normal operating temperature and things like that. So all these things, if you can collect all the signals, you can model the behavior of the machine so that if anything goes wrong in that equipment, or if it's not operating in the normal conditions that you expect it to operate, you can predict that something is going to go wrong, and you can preemptively go order the parts so that you don't have any downtime. So this is one interesting area where we've been doing some work around modeling and building pipelines for things like that using Kubeflow. And I'm going to talk about it a little bit with you guys. So I think most of you know us. We're an artificial intelligence solutions company based out of Dallas. We do a lot of AI solutions. Basically, we try to understand the problem companies are trying to solve, and we find out ways of like solving the problems for them. We build a lot of models in the process, and at the end result is to operationalize the process so that it's repeatable, you can deploy and things like that. So, like I said, this talk is going to be centered around application of AI in manufacturing and industrial processing plants. So, manufacturers can use AI to improve every aspect of their business, from equipment safety checks, because if any equipment is malfunctioning or something is going wrong, and you unknowingly go interact with that equipment at that point in time, it could be life threatening. It could cause any form of danger. So being able to preemptively understand what could go wrong with the equipment by gathering all these signals and stuff like that will help. Basically, quality design, product design, and quality assurance too is another area where AI is very important. You can guarantee the quality of the product coming out of the manufacturing plant because there's consistency. So anytime something goes wrong with the equipment, it basically affects the quality and stuff like that. So being able to handle all these things are very important, and things like that. Then there's a process called digital twinning right now, which is a very interesting concept where you can actually study the normal operating behavior of the equipment, the way the equipment behaves outside, and I mean in real life, and you gather all this data, and you can build a digital simulation of the equipment in the virtual world. So there's I mean you can do that with like AI and ML as well, where you're basically gathering all this data and you're modeling the physics and the dynamics of the equipment and things like that. So with automation, you can make smarter decisions and better decisions and smarter automations. That means you can automate a lot of all the plants. You can do things a lot more better. You can make sure that the equipment operates in the right conditions and things are working properly. That's the advantage of using AI and ML to capture and read all this data. Better decisions, you can preemptively make all these decisions as fast as possible. So that's the advantage of this in industrial applications, where you have all these heavy equipments and heavy machineries that cost millions of dollars to like install, move around, or service and things like that. So a quick overview of the problems, the gravity of all these things. Basically, maintenance takes an average of 19 hours a week. So if your equipment goes down and you didn't plan for it, it takes about 19 hours. Well, like 19 hours of work time that you could have used to like do some other things. So basically, being able to handle all these things and make sure that your equipment are behaving properly, you can preemptively determine if something is going to go wrong. I think it's very important. So operators at the same time are responsible for managing dozens of process signals, adjusting controls and settings. So think about all the things that an operator learns over the lifetime of the equipment. So as a new grad or a fresh employee, learning all these things takes a lot of time, but you can basically operationalize this and train a model to basically help with a lot of all these things as well. So with AI, you can monitor the machine performance in real time. So as the signals are coming in, you're gathering all the data and you can use it as your training data. Once you've done that, you can do prediction of anomaly in case something is going to fail or something is going to go wrong. You can handle all those anomaly and things like that. And once you have all these data points and all these model data sets that basically flows into your plant, you can predict when your equipment is due for repair. So you're not doing anything haphazardly. You basically can control, schedule, know when to do repair, know when to order a part, and things like that. So a lot of all these things add to your operational efficiency as an organization, because you basically know when to do things and how to do things right. So that's one of the important things that we can pick up from this once you start applying AI and ML in all these heavy utility areas, especially in all these big plants where they produce every day. They need to keep on running so that they can meet the demands and supply, meet the demands of the customers and things like that. So one of the goals of the problem we try to solve in this use case or in this project was to be able to build a predictive maintenance model for industrial processing plant. Well, the goal is to predict the likelihood that a machine will fail and prevent the failure through regular scheduled and corrective maintenance. So I want to be able to tell you that if you have a machine running and there are thousands of components in that machine, that this component is likely going to fail. And if it fails, I want to be able to tell you, like maybe days ahead, because the way all this machine works is like there are a lot of redundant parts, so that if something fails, the other part can still be working. So you might not be operating at 100% efficiency, but you can have 60% and things still look good. But well, if we're picking up all the signals and we know all the normal operating conditions, we can basically we can easily model all these things and know like, okay, this equipment is about to fail. Let us go and order this part. And maybe the part is manufactured in another part of the world. You can preemptively order it. And by the time the part arrives, you can replace it without experiencing too much of a downtime. Unlike if you didn't really know these things and you're operating blindly, and something goes wrong, then it becomes a big deal to fix all those things, to get things together and stuff like that. And industrial process plants are complex. A lot of all these systems contains a lot of other subsystems that are connected together and talking to each other and stuff like that. So the whole deal is to be able to like extract all these data points. Every time this equipment is running, you get all the data, all the events, you stream it to a backend utility server where you can actually take all those data and use it to train a model and stuff like that. Then once you've done that, you can now start doing condition monitoring and anomaly detection. And you can evaluate how long the equipment is going to take to get to where it needs to, uh, something needs to be replaced. Or if something is operating like it normally should not, then you can easily go in there and try to take care of all those things. Um, then the other interesting thing is like you need to know when to replace an equipment and know when to replace it. So that's called the remaining useful life cycle of the remaining useful life of the machinery. So is it what it's replacing another part while you're doing this other part replacement or fix? Because you want to know if that part is due for replacement so you can know how long it's been operating, what you need to do, and stuff like that. So all these data points are what you can get out of all these equipment, and there are millions of data points every time all these machineries operate that we can use to build a model that predicts all these things, and we can intelligently make a recommendation to the users and the operators preemptively and stuff like that. So what this means for machinery, 50% less downtime if you're building all these models. These are things that have been statistically proven, and up to 40% increase in lifetime value of the machine. So if you're doing regular predictive maintenance of the equipment, you basically enhance the lifetime of those machines, and that transforms into several millions of dollars. So anomaly detection in this industrial plant can basically indicate critical incidents like changing machine behavior. So normally we ignore things if we think it's not a big deal, but something small can become bigger if you don't take care of it over time. So the goal is to basically take care of all these kind of behaviors over time and try to see how you can mitigate it in the long run and prevent all this kind of stuff and things like that. Anomalies in machines can always be detected if the parameter in question crosses a predefined threshold. So over time, you know the normal operating conditions of all these plants. And if something goes above the threshold or below the threshold, it may trigger damage to the machine, and you need to like quickly look into it. And sequence of all this anomaly and behavior basically indicate that something is wrong in the operating pattern of the machine, and there may be a symptom of eventual possible failures around it. So the other interesting concept that we explored as well is the concept of digital twin. So think about all these equipment as just it's underlying all this engineering and a bunch of physics. Like you have rotating parts, you have parts creating temperature change and all those things. So you can do thermodynamics modeling and things like that. You can model the physics and the behavior of all this equipment. So the goal is to be able to like create a virtual digital simulation based on all the events that you're gathering out of all this equipment. So you can create a model of what's going on in real life. So you can basically take this equipment as it's running, you're gathering all these signals and digital events coming out of it, and you're creating a representation in a virtual world. So if something is going wrong, you can quickly go back and see what's going wrong and you can fix it. Or you can basically understand, because the way equipment behaves in real life is different from what you might have imagined when you were building all those equipments and stuff like that. So with digital twin, you can basically gather all these data points, study the behavior and model it. And if something is going wrong, you can basically correct it. Or if something that you did in version 1 of the product is not behaving, let's say the way you couple things together is creating more thermal heat effects at a particular point in the device or the equipment, you can basically take all this knowledge from the digital twin model that you've built. And whenever you're creating the next version or the next release of the product, you improve on it. So that's how all these companies building all this heavy equipment and all these different kinds of things. Even cars, they can model all these things and be able to improve in the next version. And that's why you have version 1 and version 2 and version 3, because by doing all this, you're getting more intelligence out of the normal operating conditions, and you're taking it back and you're using it to better improve your products and stuff like that. So this is a typical workflow. I think a lot of you probably have seen this before, but I'll go over it for people that are just getting into this. So you have all these sensors, which could be any kind of sensors, coming in and taking all this data. So you have the data processing, the data acquisition, pre-processing, building. Once you acquire the data, the next thing is to now you clean it up, make sure everything is all well formatted in the form that your model can take. And you take that data, you do algorithm model selection to know the kind of models you need to use. You run the model training, and once the model training is done, then you can do your model testing, validation, normal stuff that we've been doing or we've all doing in ML, but we're trying to operationalize this, and all these things are happening in real time. So you're having all these streams of sensor data coming in, you're analyzing it, you're deriving intelligence from it, and you're feeding it back to make inference in real time. So if something is going wrong, I can notify the operator to stop the equipment, that something crazy might be going on. And stuff like that, rather than you operating blindly, you don't really understand what's going on, and you're trying to rely on your knowledge and experience and things like that. But with this, you can gather all these metrics, all these data points, and be able to better and effectively recommend what should be done or what should be fixed to the operators and things like that. Then normal stuff that we do after training the model is to put it up for serving. That's where we do the inferencing. So as a data point comes in, we can inference and return the results and make a suggestion or a recommendation with a certain degree of confidence that, okay, I think this is what's wrong. I think this is what we need to fix, and all those other good stuff. So one of the things we did, because this is a time series data, is to use LSDM, which is a form of RNN that allows you to model time series data. Because if we're trying to observe something and predict if something is operating correctly or not, you need to have historical precedence. So if I know what you've done in the last 3-5 years, I can predict what you're likely going to do in the next 2 to 3 months. So over time, as this equipment operates, we gather all these metrics, we gather all these data points. So we have all the historical precedence, and we use LSTM autoencoder and modeling to basically model the behavior, and we can predict the normal operating patterns of the equipment. So if anything goes out of the threshold, we define a threshold. If anything goes out of that threshold of the normal operating pattern, then we can treat it as an anomaly. So LSTM model, I'm not going to delve too much into this, but LSTM uses an input time series data to both reconstruct all these events as well as predict and classify an event as an anomaly or if it's operating in the normal operating conditions. So LSTM is a subtype of RNN, which basically allows us to build a memory-based model that can understand things based on previous occurrence of the event in the past and you have different memory. Depending on how you construct your LSTM, you can basically look back as far back as maybe days, and you can, based on that, you can predict what's going to go on in the future and stuff like that. So this is a sample sensor reading where the sensor data flows in, and every time the sensor's data flows in, we can predict if it's operating normally or not. So what you see is like the sensor data is basically predictable. You have the torque, you have the normal operating conditions, you have how everything is operating. So the goal is to predict if something is out of range or it's not within range. So once you do that, you can know, okay, this is working correctly or this is not working correctly and stuff like that. So I think this was a torque measurement from the equipment that was picked. And we're basically calculating, we're basically looking at the time series data, you plot it out. You can easily see over time how the equipment is behaving and if there's something that needs to be changed or not. So this is just a little bit more into LSTM, how LSTM works, basically taking all the sequence of events and making sure everything is working correctly as expected and stuff like that. Then the inputs, the way the gating and everything works in LSTM. I won't go too much into details on this, but basically that's the model network steps that the LSTM follows and the way things are modeled so that the cell can pick in data. And once the data comes in, you can feed it to the next step and you can predict and autocorrect and things like that. I'll go into the LSTM autoencoder model for the anomaly detection. So basic steps, you train an LSTM autoencoder normal data. You take in new data points and try to reconstruct it using LSTM autoencoder. So as the data comes in, you train all the new data points, you try to reconstruct the behavior of the equipment over time in the future time steps. And you set a threshold. So if anything goes above the threshold or goes below the threshold, you can basically tell it to like go, you can basically know that it's an anomaly and you can classify as an error. So you have your threshold in normal operating condition. If anything goes above the operating conditions, it's an anomaly. If anything falls within the range, then you know, okay, this is a normal behavior. So with the LSTM autoencoder, every data that comes in, you can use to like basically do all these things and stuff like that. So and you can, once we've done that, you can basically have an error point that you can basically use to like say, okay, this thing likely is gonna fall. You can classify things as an error, or you can classify things as normal operating behavior of the machine. So so this is the reconstruction of the error and anomaly. You set a threshold. So you can see over time, once we train our model, you have the normal operating conditions. You have the places where they're likely going to be an error. And in some cases, it could be because of the way you've done your model, the way you scale things out. So you basically evaluate all these things and say, okay, is something operating out of the norm? But in this case, you can see like, okay, this looks like an anomaly. Something is going wrong in the stages and this stage, and these are still within the threshold, but it's worth looking into. But over time, once you train your model, you can identify all the spikes and know like, okay, this is likely going to be an error and something that you need to fix. So there was gonna be a demo that comes with it, but I wasn't prepared for this. So maybe in subsequent presentation we'll be showing the demo of how all these things work. I'm working from home this weekend, so I couldn't get to the office to show you the demo. So, but this is a screenshot of how everything will look once we've done the training. Basically, normal things that we do: create the model training. We're running through the Kubeflow pipeline, but I think this is a wrong screenshot for this, but this is similar to what we have. So thank you guys. I think that's it. Any questions?
Thank you very much, Charles. I'm sure there are a lot of questions. And I'm sure our students are still in the in the world of wow. So these things are possible. So guys, you can start sending in your questions via Slido, via the chat boxes on YouTube and on Zoom. But before then, I want to also let you know that this kind of presentation is one of a kind. Remember that Charles has vividly explained to us what the invaluable role of AI and ML in the manufacturing industry. So send in your questions. Charles is willing and ready to take them. So I leave the question and answer session now to Gurav, who will read out the questions to you, Charles.
That was really an insightful
Okay.
session. Like how we can use LSDM encoders in monitoring performances, AI in manufacturing field. It's really a wonderful topic. So I'm still waiting for the questions of the interns. Uh, in the meantime, I would like to ask one question on behalf of all the externs. I think they might having this question. So what would advice you will give to a student who have just began in the field of data engineering and like want to explore more about Kubernetes, Kubeflow?
I think the one advice I would give is to be like stay curious, try to know a lot of things about what's going on, understand it, and once you understand all these things, you can basically migrate this concept to other things. So a lot of all the things we do, sometimes we ourselves don't know the solution. We just go in, we understand the problem, and once we understand the problem, then we try to go through multiple iterations of how to solve it. So one thing you can do to help yourself is to basically get the necessary skills, know how to build all these models. That's essential. You don't have to have an industrial plant to build a model. You can always grab your data from Kaggle. Then the other thing you can do after that is to start building, simulating all those things, gathering all this data, creating pipelines like we've done in the previous cohorts in this MOE training. So try to do all those things yourself so that by the time you get the real data, you get exposed to the real world and you need to apply all these things. You have the necessary skill set to do what you need to do.
Thank you so much. Another question I'm having from YouTube is from Oluwaluwo Ogunisi. He says, this sounds too technical, the whole presentation. Can we get the slides afterwards this session?
I will share the slide with you. I will pass it out to the I will drop it on the MOE channel, so I will. You guys can grab it. Yeah.
Okay, thank you so much. Another question I'm getting as anonymous question from Slido. Is data science a necessary prerequisite for machine learning? I have no data science background whatsoever. Do I need to learn data science first and then jump into machine learning?
I think all these things are interconnected. So data science is basically the necessary skill, which involve a little bit of math, programming, wrangling data, and building all these models. Then once you build all these models, you want to be able to deploy it and run it at scale. That's when you start touching data engineering, machine learning, ML ops. So I'll say just start from one. All these things are big concepts. So if you can start from the machine learning side or the data science side, everything touches each other. And you're going to be working in a team. So don't expect yourself to know it all. If you're working on a part of it and you need some help from someone doing some other part of it, you can always reach out to them. And over time, you can build your knowledge base. You can know where to ask for what you don't know, and you can help people that needs help with what you know.
Okay, so I think it's like a spider web, just all connected. Do it one by one. Okay. So next question from Zoom chat I can see is, do we need to build model using LSTM for our externship, or is LSTM just a choice?
It's a choice. It depends on the problem you're solving. So in this case, we're solving a time series data. You can do things like this with ARIMA and other time series based model. But LSTM is one of the recent models that are out there, which is based on RNN, which is part of deep neural net. So it's a lot more accurate. And if you're dealing with if you need to build a model that takes in a lot of input data points, and you need to do things like classify things, remember things, and stuff like that based on the historical precedents, LSTM sounds like something that will produce a good result for us. That's why we went this route. So, but before you basically build a model or solve a problem, you need to understand the kind of problems you're trying to solve and the right kind of model that you need to use.
Yeah. So another question jumping in from Slido as anonymous. It's related to the choice of programming language. The person asked, is Julia better for data science machine learning than Python?
Um, I mean, you can use whatever solves the problem best for you, but my suggestion would be to stay with Python. One, it's open source. Two, a lot of people out there using it. So if you have any problem, people will be out there to help you solve the problem and things like that. So I'll stay with Python as a recommendation in terms of how things are going. Now, don't take that as a gospel truth. Something better may come up in the next few years, but for now, I think it's safe to stay with Python. A lot of all the frameworks out there and a lot of all the things we do is centered around Python. So I recommend it for anyone.
Okay, yeah. So another question is, what application can we use to uh, ML incorporated digital twin model? So it's been asked by Akin Pelum.
Can you come up? Can you say that questions again?
Okay, so the question is, what application can we use to ML incorporated digital twin model?
The digital twinning is basically it comprises of a lot of stuff. So think about it this way: you're trying to send out events every time you're operating the equipment. It could be your cat, and people are doing it with cat right now. We're doing a project with a cat company up here, and one of the things that they're doing is gathering all the telemetry data. So the whole idea is for you to stream all this data out of all these equipments, and sometimes it's not something you as an individual can do. It's mainly what all those companies want to do and how they design their equipment. So every time you fly a plane now, I mean, every time the plane lands, they download the data around the plane and they can predict if the plane can make the next flight. So all those kind of things are what you do with digital twins. So think about it as every time you're driving your car, you're sending out signals, and based on that signals, you're computing and visualizing how that car is driving, what direction the car is going, what velocity, and if the car is climbing a hill, if it's making a turn, if it's skidding because of snow, and you can basically use that to construct a 3D diagram of the car and know how the car is behaving. So that way you can know, okay, this part of the car needs to be fixed and stuff like that. So in terms of how you implement it, there are many things to that. You need to be able to stream out the data, and once you stream out the data, you need to be able to reconstruct it. It's a little bit more complex and something beyond me myself, but I think I've done some part of it, and I'm really interested in exploring it a little bit more further. So if you have any questions on it, I can send some more technical article. Just reach out to me on the Slack channel.
Yeah. Thanks. Another interesting question coming from Oluwasayo on Zoom chat. Given that sensors are continuously gathering the data in this use case, how often is model training usually done for detecting anomalies in time series data?
That's a very good question. So the sensors are basically bringing in the data, and every time they bring in the data, think about it as an intelligence. So think about it this way: the more I know you, the more I can predict what you like and predict your behavior, and basically tell the kind of person you are. So over time, these sensors are bringing in data from the equipment and they're saving it. So you're acquiring this data. So the way we do it is like we basically schedule a training. So one of the things you can do with Kubeflow is to have a scheduled training. It could be daily, depending on the volume of the data, or it could be weekly. So as you gather more data, you retrain. And one of the reasons why you do that is like the equipment behave differently depending on the age and when you acquire it. So initially when you acquire the equipment, so everything is still getting started, it kicks in. Then the next few years, the equipment start behaving. That means the equipment is behaves a little bit more different until it gets to towards the end of the useful life cycle of the equipment. So what you're trying to do is to gather data, the most recent data that basically tells you the identity of the equipment in terms of how it behaves. So um, you need to like constantly retrain your model to prevent model drifting, because if you train a model on data that is not more recent, like historical data, the data coming in recent time may be a little bit more different from what you train the model on. So that will create a model drift. So what you need to do is to constantly retrain your model to act based on all these new data points you're getting in, and you use it to like predict or forecast the next 2 3 weeks and stuff like that. So the way I would recommend you go about this if you're trying to implement something like this at scale. And that's the way it's done generally in the industry.
So next question coming from Slido is how do you deal with overfitting in your models?
How do you deal with overfitting in your models? Like the way you normally deal with it, basically, you don't want to train on the same set of data that you're using for testing. So that means you train your model, you create multiple models. Sometimes you basically auto select the best model based on the name parameters you're doing. But as you're training, you're basically separating the data that you're using for testing and training, and you're not basically not feeding the same thing inside the model. So the whole idea is to get new data, you split it, you train, you test with like 30% in 70% for training, you do validation, and if everything is okay and it's meeting the right RMSC, then you promote the model into production and you continue the step iteratively weekly. So, but the cool thing is like you can operationalize all those things once you've created your algorithm and you have your data streaming in.
Yeah, I hope that answers the question. Next question is for the time series data, how do they work in production, or and how does the one get inference from them? Could it be batch processing or stream processing? Could you like just please throw some light on it?
The time series data, how does it work in production? So basically in production, you have a sequence of data coming in. So there are a lot of other things that goes into play. Like as you're acquiring this data from the sensor, you need to post it. You're basically uploading it. So, but sometimes the rate at which the data is coming in might be different. You may not have enough compute resource to process the data point right away. So you have things like Kafka queues or message queues where this data come in. Once you get the data, you ingest it. And once you ingest the data, then you can now start retraining. You can have a schedule for your training. And you have a schedule for like deploying the model. So it could be like every other night. Once you train your model and you store the model and you think the model is okay, you promote the model and you drop it in production.
Okay. Uh, yeah. Next question is how do you approach projects when there's no guarantee of the outcome, especially if there's a evaluation metric threshold you are targeting?
I think one to solve any of this problem, you need data. So the one thing you try to do when you're getting started is you don't just go right away and start implementing the algorithm. You need to look at the data. So we do a lot of data exploration, feature engineering, data preparation. So if I'm trying to build a model for you or I'm trying to operationalize your process, one thing I'll do is to try to understand what kind of data do you have. Can I go inside the data? Can I exploit? Can I go in and get more details and facts around your data? So based on what you have in your data and your data points, I can know if this is going to be feasible for the most part or not, or if you need to give me some extra data points. So if you've not been collecting data from your equipment for like maybe few months or years back, there's no way I can build your model if you call me right now to predict what's going to happen tomorrow. But all these things are based on data points which is kind of like if you think about it, it's like experience. If you don't have experience, you may have a skill, but you're not going to do well with it. So there's a part of having the right data, which is very important, and collecting the data, preparing the data, and there's the other part of you applying the model to solve the problem based on what you're saying.
Yeah. Another question coming from YouTube is application environment that one can use for digital twins designing, like for example, Kubeflow, MATLAB, etc. So could you like just speak about it?
Oh, okay. So digital training is a little bit complex. So it involves a lot of things around visualization as well. So it's not just acquiring the data, training the model and stuff like that. So the whole concept is like all these data points are coming in and you want to reconstruct it in 3D in near real time. So as the equipment is sending in the signal, you're acquiring the signal and you're playing through the data points. So let's say you have a machinery that rotates at a certain degree, at a certain torque, and you have a part that is moving at a certain velocity in a particular direction. So every time step, we get a discrete signal of the events, every step of the event coming in. So as it comes in, you can now remodel it and create a 3D animation, which basically represents what they're seeing in the plant, what the plant is doing in that, near real time. So as you get all these data points, you can reconstruct it back and play through it, and everything animates and behaves as if you're basically interacting or looking at what the plant is doing. So it's basically being able to reconstruct all these data points. So the number one thing is to acquire all these data points. Then the next thing is to see how you can just play through the logs. And once you play through all these events, you can basically reconstruct it. So it's a little bit more complex than just normal data science or data engineering. I won't say it's complex, but it involves another kind of skill set, which is visualizing, animating all these things, getting the data, creating a 3D representation of it, and stuff like that.
Yeah, thank you so much. And last question for this webinar from Mustafa on Zoom chat. It's with digital twinning, collecting signals through sensors and all that stuff. Does it mean that we'll be coding chips during the externship?
Can you repeat the last part? I didn't get it.
Okay, so like the person wants to ask, does it mean that we will be coding chips during this externship program?
I think we can add it. I don't think we have it right now, but if someone wants to do it and is interested, we can make it a project for them.
Yeah, nice. So I think that was the questions for this webinar. If you still have more questions, just connect on Slack. We all are there for with answers to you. So, like wrapping up the session, I would like to invite Sophia to give the ending speech.
Wow, we've come to the end of this wonderful webinar. And I want to say a big thank you to Mr. Charles Adetule for that insightful session. I'm quite confident that our students have had a great time. I've learned a lot, and all thanks to you, Mr. Charles. To our students, thank you for your time. I urge you to keep learning, keep collaborating, and of course, keep your questions coming. We'll be glad to respond to them. Just a gentle reminder to complete the Freemium 1 course and other freemium courses that will come your way in the coming days. Collaborate and network with other members of the learning community, and network with everyone that is part of the community, and take advantage of the discussion panel on the Harmony platform. Thank you, everyone, and enjoy the rest of your weekend. Bye.